Hi everyone, you are welcome to thermodynamics class and it's a pleasure having you here today. In today's class, we are going to be looking at the first law of thermodynamics as it is being applied to flow process. In thermodynamics, the first law is a confirmation of energy principle which states that energy can neither be created or not destroyed but can change from one form to another. And this law is expressed mathematically as change in Q equals to change in E plus change in W, where delta Q is the change in heat and delta E is the change in internal energy as well as delta W is the change in work done. However, many practical applications of the first law of thermodynamics as it is being applied to flow processes are they are used in turbines, they are used for pumps, compressor, boilers, heat exchangers, among others. Now, steady flow energy equation. Steady flow energy equation. Steady flow energy equation is abbreviated as SFEE. A process is said to be steady when it fulfills these three conditions. Number one, the mass flow rate at the inlet is the same thing as the mass flow rate at the outlet. Then also, when some fluid properties such as velocity, pressure, density do not change with time, such process is also known as steady. And lastly, no accumulation of mass or energy outside the device. Energy forms in a flowing fluid. We have 4 or 5 types of energy that occurs in an open system. The first one is kinetic energy. The second one is potential energy. The third one is flow energy. The fourth one is energy in transition, which comprises of heat and work. And the last one is internal energy. Now, these are sets of forms of energy that occur in a flow system. Now, we want to derive the steady flow energy equation by adding all these forms of energy together. That is what will give us the steady flow energy equation. As we all know that kinetic energy is given as half mv square, the potential energy is mgz, the flow energy is mpv, then heat is mq, and work is mw. Then the internal energy is m multiplied by u. Now, what we are going to do now to form the steady flow energy equation is to add up all the energy. Now, let's consider an open system, just as what we have on the board. If this state is state 1 prime, and here is state 2 prime. At this level, we have P1, we have V1, we have C1, and the same thing here, we have P2, V2, C2. Then from this point, this is the datum line. From this point to this point, this is Z1, And from this point to this point, we have Z2. Now, going by what I have just said earlier on, that if we want to form the steady flow energy equation, we need to add up all these forms of energy. We need to add them together. So we are starting with kinetic energy. We have half mc square. Let's change this to c. Half mc square plus the potential energy is mgz, which is for state 1. If you look at this system is showing us that there is something that is entering and something is exiting. So once one prime is representing the inlet, while two prime is representing the outlet, the exit of the system. Now we need to now write the steady flow energy equation at state 1 and state 2. State 1 is the one that is entering, while state 2 is the one that is leaving the system. So at this level, the mass flow rate at point 1 is the same thing as the mass flow rate at point 2. So therefore, we have half mc1 square plus mgz1 plus the flow energy mp1v1 plus its mq1 to 2 plus mw1 to 2 plus u plus mu1 equal to the state, the exit state. The first one that we have written is representing for the inlet. And we need to go back to the outlet level as well. At the outlet level, we have it as 1 over 2 mc22 plus mgz2 plus mp2v2 plus mu2. Now, what we are going to do now is this. If you look at the left hand side equation, the inlet, which is representing for the left hand side, and if you look at the outlet, which is representing the second equation, you will notice that there is something that is common for both, which is the mass flow rate, as we have said earlier on, that there are some conditions for the inlet and outlet. The mass flow rate is constant throughout the process. If you notice, both energy in transition, which is heat and work, they are not occurring at the outlet level. I have already taken it into consideration at the inlet level, whereby they have it as mq1 to 2 plus mw1 to 2. Now the mass flow rates for the left hand side and the right hand side are equal, so we need to eliminate the mass flow rate out of this equation. Then also, enthalpy is a thermodynamic properties which is defined as a combination of internal energy and the flow energy. So we go back to this equation, we eliminate the mass flow rate out of it. Then for the internal energy and the flow energy, we merge it to a single term which is known as enthalpy. So the left it half C1 square plus GZ1 plus this gentleman marries to this gentleman. It becomes H1 plus Q1 to 2 plus W1 to 2 equals to half C22 plus GZ2 plus H2 plus H2. So what we have on the board, if you are making the heat transfer or the work transfer as the major determinant that you are asked to determine, what you have on the board is already being expressed as the steady flow energy equation. So this is the steady flow energy equation. Now we are now going to streamline this equation into some of the engineering devices in which first law of thermodynamics is being applied. What are the engineering devices? Number one, heat transfer devices, which comes in three different categories: the boiler, the condenser, and the evaporator. The second one is work transfer devices. Under the work transfer devices, we have the turbine, we have pumps, fans, compressors, among others. And the third one is a throttling devices. The fourth one, nozzles and diffusers. And the last one, heat exchangers. Having said the applicability of steady flow energy equation, they are meant for these five devices that I have just mentioned. The first one is heat transfer device, the second one is work transfer device, the third one is throttling devices, the fourth one is nozzle and diffuser, and the last one is heat exchangers. So we will now go back to the general form of the steady flow energy equation as you can see on the board and streamline it for heat transfer devices. Now, before we go into this, let's consider a simple power plant, or let's leave the power plant alone. Let's look at the steady flow energy equation as it is being applied to each of these. Now, for boiler, the function of the boiler is used to raise the temperature of a substance, which means the heat transfer in a boiler is taken as positive. The condenser is used to remove heat and throw it out to the environment. So in this case, the sign for heat at this level is negative. Evaporator serve the same purpose as that of the boiler, which is taken as positive. The turbine is taken as work output, which is positive. The pumps, fan, compressor are taken as work input. And having said this, we have done all this in sign convention, which we said work input is negative, work output is taken as positive, heat input is taken as positive, and heat output is taken as negative. So now, let's look at a simple power plant arrangement in analyzing this. This is a boiler, this is turbine, this is condenser, this is pump. Now we need to label this. This state, we call it state 1, state 2. As it is exiting the turbine, it becomes state 3. As the turbine is entering into the condenser and coming out of the condenser, it becomes state 4. Now, this is a simple illustration of a simple power plant arrangement. From this power plant, let me just give you a holistic view about it. The pump will pump the water and process it into the boiler. The boiler will heat up the water to some certain temperature and pressure. Then the boiler releases the what has already been heated to some certain temperature. It moves into the turbine at further temperature as pressure. As it is exiting the turbine, there is a pressure drop as well as temperature. So as it is entering into the condenser helps to cool the steam that is coming from the turbine and compresses it back to what? Liquid, and it goes back into the pump rather. So in this process is called a cyclic process. So it's going from 1, 2, 3, 4 and from 4 back to 1. That is the process. Now if you look at boiler, we want to start with boiler since we said a boiler is used to add heat input into a substance. Now a boiler lies between two numbers. It lies between 1 and 2. So in this case we are going to take, there are some basic assumptions that are meant for all the applicability of the steady flow energy equation in these 5 things that I have mentioned. For boiler and condenser, what happens in such case is you go back to the steady flow energy equation. The kinetic energy and the potential energy are negligible. That's number 1 assumption. Number 2 assumption is that there are no work transfer in the system of a boiler. What the boiler does is to heat up the fluid that is inside it. So we go back to the equation. Since we are told that negligible kinetic, negligible potential, so when we write out the equation, half C1 square plus GZ1 plus H1 plus Q1 to 2 plus W1 to 2 equals to half C22 plus GZ2 plus H2. Negligible kinetic energy and potential energies, 0, 0. There are no work interaction, it becomes 0. At this level too, at state 2, they become 0. At here, it becomes 0. What are we left with in the equation? We are left with H1 plus Q1 to 2 equals to H2. Therefore, Q1 to 2 equals to H2 minus H1. This is the heat transfer in the boiler. It can also come in the rate form. When it comes in the rate form, it becomes Q dot is in the rate form equals to the mass flow rate multiplied by H2 minus H1 in rate form. Next one we are going for is the condenser. As we all know that what the condenser does is to help us to remove heat. So we go back to the equation, half C1 square plus, at this level, the condenser lies between state 3 and state 4. So the kinetic energy at this level becomes C3 square plus GZ3 plus H3 plus W3 to 4 plus Q3 to 4 equals to half C4 square plus GZ4 plus H4. This is the steady flow energy equation. Going by the assumption that we have said earlier on, the kinetic energy, potential energy, and the work transfer are ignored in the equation. So what are we left with? We are left with H3 plus Q3 to 4 equals to H4. So at this level, Q3 to 4 equals to H4 minus H3. This is for condenser. In the rate form, it can be expressed as Q equals to MQ3 to 4, which is the same thing as the mass flow rate multiplied by H4 minus H3. Now, the next thing we are going for now is for work transfer device. For work transfer devices, we have turbine and we have pump. At this level, this is turbine. Turbine does work output. It supplies to a generator. Generator is the one that will give out the electricity that we are expensing. Why this one is carrying out what? Work input. So this place is positive for turbine and here is negative. So we go for turbine now. Turbine lies between state 2 and state 3. So we go back to the steady flow energy equation and bring out the steady energy equation and reduce it by following the basic assumption which are meant for it. So for turbine, we have half C2 square plus GZ2 plus H2 plus W2 to 3 plus Q2 to 3 equals to half C3 square plus GZ3 plus H3. So what are the basic assumptions? The kinetic energy are being ignored, the potential energy are being disregarded. Here, since it's a work transfer device, the system is being what? Thermally insulated. There are no forms of heat in the system. So we eliminate those terms. This becomes 0, 0. This becomes 0, 0, 0. So what are we left with? We are left with H2 plus W2 to 3 equals to H3. So W2 to 3 becomes H3 minus H2. That is for turbine. And in the rate form, it is given as Q equals to M multiplied by W, which is the same thing as M into bracket H3 minus H2. This is given as the rate form. I'm sorry, W. This is W. W in the rate form. Now for the pump, we write out the steady flow energy equation again and follow the same assumption that we adopted for turbine in applying for pumps. So we go back. Pumps lies between 3 and 4. So therefore, we have 1 over 2 4 square plus GZ4 plus H4 plus Q4 to 1 plus W4 to 1 equals to 1 over 2 C1 square plus GZ1 plus H1. Following the same assumptions, 0 becomes 0, 0, 0. So the equation reduces to W4 to 1 equals to, this one comes to this side. It becomes H1 minus H4. So in the rate form, we have W4 to 1 equals to mass flow rate multiplied by W4 to 1, which is the same thing as M into bracket H1 minus H4. That is for pump. So we are done with heat transfer device and we are done with work transfer device. The next phase is nozzles, diffusers, and throttling devices. Now I'm going to use one schematic to bring out these three things that I have just written on the board, which are nozzles, diffusers, and throttling device. Now, if the direction of the flowing fluid is coming from this side, this shows that this particular state, state 1, 1 prime to state 2, 2 prime, is taken as nozzle. From 2 to 3 or 2 prime to 3, 3 prime is taken as the throttling device, while from 3 to 4 is taken as the diffuser. So what is the definition of a nozzle? A nozzle is a steady operating device whose purpose is to increase the velocity at the outlet level at the expense of a pressure drop. A nozzle, a diffuser function is to increase the pressure at the expense of what? Low in velocity, low in the speed of the working fluid. The throttling device, they both have the same uniform diameter. So which means state 2 is the same thing as state 3. Now let's bring it out one after the other so that we can analyze it, so that we can get it better. So this is a nozzle. This is the direction of flow. At this level, we have P1, we have V1. So here we have P2, we have V2. At this level, V2 is greater than V1, while P1 is greater than P2. You can also reverse it by saying V1 is less than V2 and P2 is greater than P1. If you don't want to write it, if you don't want to dictate it or give an explanation, since engineer, we do communicate to one another by drawing. If you have brought out something like this out and you use this mathematical expression to define this, the person that is reading will understand that what you are only trying to pass across is you are talking about a nozzles. Now, for the diffuser, you can see it diffuses, it spread. If this is the direction of the working fluid, if the arrow is changed to this side, it becomes a nozzle. But if the arrow is coming from left to right, it becomes what? A diffuser. So at this point, we have 3, 3 prime, 4, 4 prime. So what happened at this level? We have P3 and we have V3. We have P4 and we have V4. At this level, P4 is greater than what? P3. So what happened to V3 is greater than what? V4. So if you have something of this form, you have passed a message that this particular thing that you have here, which is a diffuser, a steady operating device, has been defined as this. You have passed a message across. Now let's look at the steady flow energy equation in these two things that I have just mentioned. So write out the steady flow energy equation, which is 1 over 2C1 square plus GZ1 plus H1 plus W1 to 2 plus Q1 to 2 equals to 1 over 2C2 square plus GZ2 plus H2. Now, what are the basic assumptions that you need to take? The assumption, what you are only left with is kinetic energy and the enthalpy. Every other thing will be eliminated. So the first assumption is the potential energy is being disregarded, taken as 0. There are no work interaction in the system. This is thermally insulated. So therefore we have GZ2 to be equals to 0. So we are left with 1 over 2C1 square plus H1 equals to 1 over 2C2 square plus H2. This is meant for nozzles. Now for diffuser is at state 3 and state 4. So we write out the steady flow energy equation once again. 1 over 2 C3 square plus GZ3 plus H3 plus W3 to 4 plus Q3 to 4 equals to 1 over 2 C4 square plus GZ4 plus H4. Taking your assumption, GZ3 becomes 0, W34 becomes 0, this becomes 0, and this one becomes 0. So the steady flow energy equation for now for the diffuser, we write out the steady flow energy equation again. The diffuser is at state 3 and state 4. We have 1 over 2 C3 square plus H3 plus GZ3 plus W3 to 4 plus Q3 to 4 equals to 1 over 2 C4 square plus GZ4 plus H4. Taking the same assumptions that you took for nozzle, the first one is negligible kinetic energy, the negligible potential energy. There are no work transfer, there is no heat transfer in the system. So this one becomes 0, 0, 0. The same thing also applies to GZ4. So the steady flow energy equation reduces to 1 over 2 C3 square plus H3 equals to 1 over 2 C4 square plus H4. This is the steady flow energy equation for a diffuser. Throttling device, it lies between state 2 and 3. So at this level, since the diameters are uniform, going back to the continuity equation is telling us that since the diameter is equal, definitely C at this level will be equal to the other side. So we have for throttling level will be H2 equals to H3, after we might have taken all the various forms of assumptions that are required in the calculation. Number one, we eliminate the kinetic energy, we eliminate the potential energy, we eliminate the work transfer, we eliminate the heat transfer in the process. Therefore, the equation now reduces to H2 equals to H3. Don't forget that your enthalpy, it has a relationship between specific heat and temperature, just as the H equals to CP/dT. Therefore, this gentleman can also be represented as CP into bracket T2 equals to CP into bracket T3. CP cancels CP. So the temperature at this level equals to the temperature at this level. So this is the steady flow energy equation for a throttling devices. Now let's take an example based on what we have been doing since. Let's solve work example as related to what we have been doing. Example 1 is on adiabatic nozzles. Steam enters a nozzle at enthalpy H1 equals to 2,800 kilojoule per kilogram and speed V1 equals to 50 meter per seconds. It leaves with enthalpy H2 equals to 2,600 kilojoule per kilogram. Full stop. Neglect potential energy and shaft work. Heat transfer Q equals to 0. Determine the exit speed V2. We are going to follow our normal ways in solving problems. We are starting with step 1. Our step 1 states that we should bring out the parameters, the given. At this level, they are talking about nozzles. It enters and it is leaving the nozzle. Entering is represented as subscript 1 and exiting is represented as subscript 2. So the enthalpy at the entering is what? H1 equals to 2,800 kilojoule per kilogram, and the speed is given as what? 50 meter per seconds. At the exit, H2 is given as what? 2,600 kilojoule per kilogram. So the next step, we are asked to define unknown. Step 2, we are asked to determine the exit speed, that is V2. Then going back to our ways of solving problem, we need to move to step 3. Step 3 states that we should state some basic assumptions. In the question already, the assumptions are there. Number 1, no work transfer in the system. Number 2, kinetic energy, potential energy rather, is disregarded, and heat transfer in such case become 0. Those are the 3 assumptions in the question. The next step, step 4, is schematic. We all know how the schematic of a nozzle looks like. This is a nozzle. This is the direction of flow of the working fluid. So if this is state 1, 1 prime, and here is 2 prime. At this level, V1 is 50 meter per seconds. H1 is 2,800. Then V2 is unknown. H2 is given as 2,600 kilojoule per kilogram. So write out, the next thing is the governing equation. The governing equation in this state is the steady flow energy equation. So you need to write everything out. So we have 1 over 2 C1 square plus GZ1 plus H1 plus W1 to 2 plus Q1 to 2 equals to 1 over 2 C22 plus GZ2 plus H2. This is the steady flow energy equation. Then following step 3, we are asked to disregard potential energy, the work transfer, and the heat transfer. So the equation becomes 1 over 2 C1 square plus H1 equals to 1 over 2 C2 square plus H2. Note, V1 in this case is also the same thing as C1. Wherever you set your eyes on V1, I might be mistakenly using V1 for C1. So which is also the same thing as C2. So we are asked to determine V2. So what we need to do is to make V2 the subject of the formula. So H comes to this side, 1 over 2 C2 H1 minus H2 plus 1 over 2 C1 square. So you use 2 to multiply everything. C2 becomes 2 into brackets H1 minus H2 plus 1 over 2C1 square, all in brackets. So the next step is to plug in the data that are given in the question. So C2 equals to square root of 2 into bracket 2,800 minus 2,600. Remove the kilojoule out of this, multiply it by 1,000 plus 1 over 2. The inlet velocity is given as 50 square. Final answer becomes 634.43 meter per seconds. The velocity at this level is very, very high than the velocity at the inlet level, which means the rate at which the fluid is coming out from the nozzle is very, very high. As the speed is very, very high, this shows that it is a supersonic velocity. Is that taken? The velocity is very, very high at that level. Now let's look at example 2. Example 2 is on steam turbine. A steam turbine has mass flow rate of 5.0 kilogram per second. Steam enters with enthalpy H1 with 3,500 kilojoule per kilogram and leaves with H2 equals to 2,900 kilojoule per kilogram. Full stop. Assume adiabatic and neglect kinetic and potential energy changes. Determine shaft power output in kilowatt. Solution. Step 1. Given data. Enthalpy H1 is given as 3,500 kilojoule per kilogram. Enthalpy H2 is given as 2,900 kilojoule per kilogram. The mass flow rate 5.0 kilogram per second. The shaft work is what we are asked to determine. Find the shaft work. The shaft work in kilowatts is to be determined. The next thing is assumptions. So assumption 1, the potential energy and the kinetic energy effects are negligible. Assumption 2, since it is an adiabatic process, Q becomes 0. So the next thing is we bring out what? A schematic, a turbine. Schematic. This is the turbine. Steam enters and leaves at this level. H1 is 3,500 kilojoule per kilogram and H2 is 2,900 kilojoule per kilogram. Then the mass flow rate M1, M2 equals to 5.0 kilogram per second. The next thing is to write out the governing equation. Governing equation. The governing equation is the steady flow energy equation. 1 over 2C1 square plus GZ1 plus H1 plus W1 to 2 plus Q1 to 2 equals to 1 over 2C2 square plus GZ2 plus H2. This is the governing equation. The next step is to start analysis. So going back to the equation, there are some things that we need to neglect according to the assumptions. So when we follow it, the equation reduces to H1 plus W1 to 2 equals to H2. Then W1 to 2 equals to what? H2 minus H1. H2 minus H1. So in the rate form, we are asked to determine the shaft work in kilowatts. So which means this one is in kilojoule per kilogram. We have to multiply it with the mass flow rate. So the shaft work becomes mass flow rate multiplied by the work transfer, which is the same thing as M into bracket H2 minus H1. So we plug in the values into this equation. We plug in the values into equation 1. So the mass flow rate is given as 5.0. H2 is given as 2,900 minus 3,500. So the value becomes 3,000 minus 3,000 kilowatts, which is W1 to 2. So therefore, you can eliminate the negative sign by indicating that since we are talking about turbine, you need to change the direction of the work done. So W2 to 1 becomes 3,000 kilowatts. So this is the work done, the shaft work in the system.